Okay, so now I want to describe to you a method which goes by the name generating function method, by which we are going to be able to count how many microstates there are consistent with the constraints that have been provided, namely that the total energy is fixed and the total number of particles are fixed. So, if you recall in the last several slides, I managed to do the same thing, but using a rather wasteful approach, namely list all the possible solutions corresponding to the various microstates and simply count them one by one. So, that is wasteful because it requires a lot of computational resources to list all the solutions. So, it would be far easier if there were a simpler roundabout way of bypassing the necessity of having to list all the solutions explicitly, and instead simply count how many solutions there are without knowing what those solutions are. Okay, so that is called the generating function method, which I am going to describe to you now. So, before I begin, I want to point out that the subject is going to rapidly become quite technical, and it is really important for you to be ready with a pen and some paper in hand to and follow along when I do the calculations. So, it is not like physics is not like reading a storybook where you simply just listen to some video or just read a novel. So, you have to actually follow along with pen and paper. So, let me start with the generating function method. So, it is an analytical method which allows me to solve or count the number of solutions of these Diophantine equations that I have been talking about without explicitly listing all the solutions. So, in order to do that, recall that the number of solutions that I was talking about that I am interested in is really this. So, it is sum over all the different possibilities where I am constrained by this constraint, which says that the total energy is fixed. So, I have assumed that the energies are like the steps of a staircase, they are all equidistant. So, that is why there is a j there, and this is called a Kronecker delta. So, this forces me to assert that the total energy of the system of this microstate rather is u all the time. So, and this Kronecker delta forces me to assert that the total number of particles is fixed as n. So, if you do not remember what Kronecker delta is, it is very important for you to know what this is. So, if I write m comma 0, what I mean by this is this is 1 if m is 0 and it is 0 if m is not 0. So, this is called Kronecker delta. So, after a German mathematician Leopold Kronecker. Okay, so, I am going to repeatedly use this symbol. So, it is important for you to know what that is. So, now, so this forces me to conserve energy and forces me to conserve the number of particles, but once that is forced on me, then I am free to sum over all the different possibilities, and these Kronecker deltas will keep track of whether or not energy and number of particles are conserved. Now, I really want to perform this summation. So, it turns out that an easier way of doing this is to actually define a more general object called the generating function. So, this is called a generating function, and I define a whole bunch of variables called x1, x2, x3 all the way up to x infinity, and I multiply this number that I am interested in. So, before I sum over the n's, I multiply with x1 raised to n1, x2 raised to n2 and so on and so forth, and then I sum over n. So, clearly the answer that I am looking for, if I set all the x's to 1, then I get back the thing I have circled in red here. So, it is easy to get the answer that I am looking for, which is the number of microstates consistent with the total energy and total number of particles. All I have to do is first calculate the generating function and set all the x's to 1. So, as you know already, and I have told you several times, that the total number of microstates is also the exponential of the entropy, because according to Boltzmann, the entropy is nothing but the logarithm of the number of microstates. So, that is exactly what I was talking about, that if you set all these x's that are here to 1 and then I get back the answer that I am looking for, that means the answer that I have circled here in red. So, this z of n is sometimes called the microcanonical partition function. So, what does that mean? So, micro means taking into account the detailed distribution of the number of individual marbles, for example, in the example that I gave you. So, the individual marbles on each step, and that would correspond to the micro adjective there. And canonical actually means conforming to a set of rules. Canon is just a rule book, as it were. So, partition function, the word partition is a way of writing an integer as the sum of other integers. So, for example, you can write 10 as 2 plus 3 plus 4 plus 1. So, this is an example of a partition. So, partition function is just is basically tells you how many ways in which you can partition an integer. So, in this case you are constrained also by those requirements, that the total energy and number of particles and so on. So, now how do I calculate this generating function? So, there is a clever trick to do that, and that is to invoke what is called the integral representation of the Kronecker delta. So, I want to convince you that this is nothing but the Kronecker delta. So, if I perform this integration and if k is an integer here, then this is equal to precisely the Kronecker delta. And why is that? So, suppose k was not 0 and you perform this integration, what is this going to look like? So, if k was not 0, so imagine that k was not 0, then what does this look like? So, this is going to look like e raised to I k theta over 2 pi I k, and then I have to make theta go from 0 to 2 pi. So, now because k is an integer and k is not 0. So, if k is not 0, this is not 0, and because k is an integer. So, I am going to get here I am going to get e raised to 2 pi I k, then I am going to get e raised to 0, which is 1. So, because k is an integer, this is going to be 0. So, the numerator is 0, denominator is not 0. So, this whole thing is 0. But what if k is 0? So, if k is 0, clearly then this becomes 1. So, that when this is 1, I simply integrate over theta and I get 2 pi, and there is already a 2 pi there. So, the answer is 1. So, I get the result that when k is not 0, the answer is 0, and when k is 0, the answer is 1. So, this is clearly the Kronecker delta symbol. Alright. So, now I am going to use this trick to rewrite my constraints. If you recall, the constraints involve the Kronecker delta with respect to the energy here and the Kronecker delta with respect to the number of particles. So, I am going to rewrite that as an integral representation over say, two angles like theta and phi. So, now what is the advantage of doing that? The advantage of doing this is that I bring all these n's that I have to eventually sum over into the exponent here. So, if you see here, so I have successfully managed to bring all the n's in the exponent, and the reason why that is important and useful is because the generating function also has n's in the exponent because of these x's. So, if all the n's are sitting in the exponent and then you have to sum over all the different values of the exponent, that should immediately ring a bell, and that is called a geometric series. So, we are going to make use of the fact that we know how to sum geometric series, and what we have done through this device of writing the Kronecker delta in terms of the integral form is that we have successfully converted into a geometric series. So, now you see that this is what is going to happen. So, I am going to rewrite the generating function and it starts to look like this. So, all I have to do is sum over all the n's, and then I take into account all the different energy levels here. So, now of course, I have done a clever thing here, and that is I have interchanged the summation and the product sequence. So, if you recall here, there was the summation was before and the product came later. But here I have done the reverse. I have put the summation earlier and the product later. So, the question obviously is that am I allowed to do that, and the answer is yes, because of this result here. So, if you stare at this sequence of terms here. So, you have y 1 raised to n 1, y 2 raised to n 2, y 3 raised to n 3 and so on. So, I have to sum over all the n's. So, if I sum over all the n's, I simply get geometric series, etc., etc. So, now suppose I do the reverse. So, this is like a product. Okay. So, this is just nothing but the product over j of y j n j. So, that is what y j raised to n j. So, instead of doing the product first and summing later, suppose I do the reverse. I sum each of those y j n j first and then I take the product. So, what do I get? I get precisely the same thing, because this is going to be y j, and then if I take the product later I get back the same thing. So, there is nothing lost or gained by doing this. Of course, what is gained is basically that I am able to now do the geometric series in a nice way. So, now having done this, so remember that I am talking about marbles on a staircase where there is no restriction on how many marbles there are per step. So, in which case I am allowing myself to sum from n equal to 0 all the way up to n equal to infinity. So, if you remember that I told you earlier that if these marbles represented fermions, for example, or spinless fermions specifically, that I will not be allowed to accommodate more than one marble per step, but that we will discuss shortly. But now let us imagine that there is no restriction on how many marbles I can accommodate per step, in which case I sum all the way up to infinity and I get this result. So, now all I have to do is I take into account all the steps by multiplying with respect to this index j. So, for concreteness, I had assumed that all the steps are of equal height, but I do not have to. I mean, it's very easy thing for you to understand that I simply replace j by epsilon j, which represents the height of each step. So, I won't there is no loss of generality in going from here to there. So, if the heights of the steps were all uneven, clearly this would be the answer, and this provided there is no restriction on how many marbles I can have per step. Okay, so, this is the generating function that I have to calculate. So, my main interest of course is not to get the generating function, but to get the entropy of the system, and I have told you earlier that the entropy of the system is simply obtained by setting all the x's to 1. So, in which case I get back what I was looking for, that red circled summation that I started off with. So, I set all the x's to 1, and so there is only one place where there is an x here, that is here. So, I set it equal to 1. Then what I have to do, so the entropy is here and the logarithm of this quantity is my entropy. So, if I am successful in doing this integration over this theta and over this phi, and of course, I am able to do this product properly, then I am all done. So, this is a brilliant way of counting how many microstates there are, consistent with the constraint that the total energy is U and the total number of particles is N, without having to explicitly list all the possible solutions of those Diophantine equations. So, this is a very clever way of analytically counting how many solutions there are. All right. So, now how do I convince you of the correctness of this? It all seems quite abstract and kind of intimidating, but it would be less intimidating if I were successful in proving to you or convincing you by taking some simpler examples. So, instead of looking at infinitely many steps, suppose I look at this specific example of 3 equidistant steps. So, if you recall that I have told you earlier that if the number of steps are small and the number of particles involved or the marbles involved are small, then it really is not much of an effort to list all the solutions explicitly. You do not have to, it is not, it does not take a lot of effort. So, you might as well do that. So, remember that we have already done that once for 3 marbles. And what I want to do is use this general formula for 3 steps and see if it works out to be what I told you earlier by explicitly listing all the solutions. So, now how do I work it out for 3 equidistant steps? So, here instead of taking the product over all the different steps, I only take product up to the 3rd step, and then all I have to do after doing this is that I have to integrate. Suppose I first decide to integrate over phi. How does that work? So, I clearly I can do it this way, that I can pretend that this is some kind of again I revert this back to the binomial type of form, and I expand in powers of this quantity. Or you can use your computer, you can use your favorite software to do this. Nowadays there is a lot of software which does this, like Mathematica, MATLAB. So, there is a lot of these symbolic algebra packages which you can use to do it, or if you do not want to do that, it is very easy, that just expand this out in powers of this object, just because it is sitting there, and then you know how to do it over phi. So, I am not going to do this explicitly because it is a little tedious and it is somewhat unpleasant, and but you should do it yourself. So, if you do it, you get this answer. So, now of course, that is over this this variable, this angle called phi, but I also have to integrate over theta. So, the integral over theta is similar, because think of this some kind of a quantity in whose powers you decide to expand, and expand this whole thing in powers of e raised to minus I theta, for example, and then you integrate over theta. And when you do that, you get this rather nasty looking expression here, which involves what is called Heaviside step function. So, if you do not really follow all this, it really does not matter all that much, except that I am just using it to convince you of the correctness of this general formula here. So, if you are already convinced, this specific example is not really that important, but nevertheless it is worthwhile, it is instructive to go through at least one specific example. But as you can see, the final answer even for a 3-step problem is not easy, especially because I have not constrained the number of particles n. So, n can be as large as it wants. So, and u can also be as large as it wants, only the number of steps are 3. So, that is the reason why it is a little bit more complicated. So, this involves what is called Heaviside. So, this is called Heaviside step function. So, this symbol, I am going to use this symbol consistently throughout, and this is called Heaviside's step function. So, Heaviside was a English mathematician. His grandfather apparently was part of a rugby team, and that team was called Heavisides, and his grandfather decided to take that as his last name. So, that is why it is called Heaviside. Okay. Now, I am going to plot this versus the total energy of the system versus entropy. Now, I am going to now specifically focus on the 3 marble examples. So, I have already committed myself to studying 3 steps. So, in addition, I am going to say that there are 3 marbles. Now, 3 steps, 3 marble systems, we have explicitly listed the solutions by hand some time back, and at that time we got this plot. So, if you rewind and go through the slide that I had described earlier, it was precisely this plot. So, the entropy was 0 if the energy was 3 in some units. So, I mean in the units that the energy of the first step is, say, the energy of the first step when there is 1 marble sitting on it is 1. So, if you use those units in that case, so if the energy was 3, the entropy is 0. If it is 4, it is still 0, but if it is 5, it starts to become non-zero, and 6 it is non-zero, 7 it is non-zero, then 8 again it is 0, because there is crowding at the top. If you remember, that I explained this to you, why entropy starts to fall, and because the number of available states when are limited, because you have reached the top step already. So, if the number of steps is fixed, then the entropy starts to fall. So, then it becomes 0 again. So, this also has this example that the entropy kind of is non-monotonic. That means, it kind of goes up and then comes down. So, the temperature is positive here, negative there. So, this is an example where the temperature can be both positive as well as negative. but then I repeated this 3-step 3 marble example to convince you of the correctness of this analytical formula. Okay, so now let me ask another question, and that is, this is an important concept. It is called the concept of extensivity of entropy. So, if you remember in some of the earlier slides, I tried to explain to you why we take the logarithm of the number of ways of arranging the microstates, and that is because the number of ways of doing that, I told you, balloons up exponentially, but then by implication the logarithm should actually be linear. So, if I say linear, you should ask linear in what? So, linear obviously in the size of the system. So, if the entropy is linear in the size of the system, that is a property known as extensivity. So, in this small paragraph, I have explained to you that variables such as temperature, I have not properly defined it yet, but I am going to do it shortly. So, assuming you know what that is from your earlier knowledge. So, temperature are total internal energy, volume, entropy, these are the various quantities that we wish to classify as either being extensive or intensive. And the way to classify them is to double the size of the system and ask yourself, do these quantities also double or do they remain the same? So, if they double along with the size of the system, for example, then you say it is extensive. If they do not change at all, you call them intensive. But then I have pointed out here in small print that the total internal energy is extensive only when the subsystems do not interact amongst themselves. But if they do interact amongst themselves, a rather hard problem, and it is not at all obvious that it is extensive, but we of course will not be discussing that those issues in this introductory course. So, what we can do is that we can decide whether the entropy is extensive or not. So, that is the question that I am going to ask myself. So, I have told you that the number of ways of arranging the microsystem balloons up exponentially. So, by implication the logarithm of that should be linear. So, that by implication therefore, that the entropy is extensive. So, how do I decide whether the entropy is extensive? So, recall that I have a general formula for counting how many microstates there are in terms of those theta and phi integrations. So, in principle I should be able to plot this ratio, for example. So, I fix the total energy and total number of particles, then I scale up the energy by factor lambda, I scale up the number of particles by a factor lambda, and then I divide by the original entropy. And if I plot this ratio versus lambda, and if entropy is indeed extensive, this plot should be linear, it should be a straight line. So, the question is it a straight line? So, obviously the proper answer to this will crucially involve how good we are at explicitly evaluating those integrals over theta and phi. So, we probably are not going to be able to do this in general, and in any event we can suspect that if the number of say particles is small or the number of steps are small, etc., the extensivity is not likely, because there is a lot of in some situation the solution exists, some situation solution does not exist. So, there is a lot of abrupt changes that take place when the number of steps are small or the number of particles are small. So, there is linearity is an unlikely possibility. However, linearity may actually be quite likely if you work in what is called the thermodynamic limit. So, what I mean by that is that I am going to ask myself, suppose I fix the total energy per particle and then I scale up the number of particles. So, extensivity demands that I scale the total energy the same way I scale the total number of particles. So, if that is the case, then all I have to do is I fix the ratio of total energy and the number of particles. So, I could denote that by small u. Small u is basically the energy, total energy per particle. So, if I fix this, then that is going to be the same as this. So, even if I scale u and n, I get back the original small u. So, now I am going to try and see if I can simplify this integration, which looks quite formidable actually in general. and see if I can evaluate this integration in what is called the thermodynamic limit. So, the thermodynamic limit is basically a limit where u tends to infinity, n tends to infinity, but u by n, which is small u, is fixed. Okay, so, this is called thermodynamic limit. So, I am going to work in this thermodynamic limit, and so recall that this S of u of n has this form, and depending upon whether I am talking about fermions or bosons. So, that means if you have marbles where there is no restriction on how many marbles per step are allowed, then that would correspond to bosons, and if there is only a maximum of one marble per step that is allowed, that is called a fermion. So, that is how it works out, and I have already explained to you why this formula comes out the way it does. And now I am going to rewrite this f in this fashion. So, I am going to rather define a new quantity called h, which is the log of f multiplied by some prefactor like this. So, as a result, then I am going to be able to write this f as an exponential with a extensive n sitting right there. So, now I am going to be able to factor out this integration like this. So, there is an n and there is something in the bracket which I am going to call w. So, eventually I will be forced to reckon with this integration over these two angles. Of course, they were still there earlier, they are still there now, but then the simplification that I have achieved is that I have pulled out this n outside. So long as I can convince myself that this quantity is now intensive, in other words, if I scale the total number of particles by lambda and I scale the total energy by the same amount, then if this does not change at all, then it is called intensive. So, if I am successful later on in convincing myself that this is intensive, then you see that all the extensivity is lumped into this n, which is the number of particles in the system. So, now I am kind of forced to reckon with this type of an integration where z is some, so think of theta and phi as some components of a complex variable. Maybe this is the real part, this is the imaginary part. So, in other words, this z, so I am going to be forced to think about this as an integral in the complex plane, where this is a function of z is described by the real part theta and imaginary part phi. Or so the point is that eventually I am forced to reckon with this type of an integration, but crucially where this n is really huge. So, now the question is that do mathematics textbooks tell me how to solve this easily? So, the answer is yes. So, in complex analysis or complex variables, there is a method called the method of steepest descent. I am going to skip the technical details for now, because firstly it is not part of this course and I have listed that as a prerequisite. Maybe if I get time later I might get back to it, but if you do not know what that is, please read your book on complex variables and go to the chapter where they discuss the method of steepest descent. But to cut a long story short, the steepest descent method says that suppose you want to do this integration and then n is really large. So, if this n is really large, then the answer to this integration is simply this. So, this I was trying to do this integration, and this integration is n. So, this integration is nothing but it's just this, it's proportional to that, and where this z star is basically the zeros of the, it's called the saddle point. So, it's the location of z where the first derivative of g becomes 0. So, it's actually a saddle point because it's minimum in one direction, maximum in the other direction. So, it's resembling a saddle. So, now those details I am going to skip, why that is the case and so on. So, please look that up from your book on complex variables. So, roughly speaking, so in the thermodynamic limit, this kind of can be approximated using method of steepest descent or the saddle point method to this expression. So, this looks very simple. So, I have to figure out what this theta star and phi star are, by simply equating the first derivatives to 0 at the values of theta star and phi star. So, and also if you ignore this proportionality factor here, then I can just read off, take the logarithm on both sides here, and I can read off the expression for the entropy of the system, which is basically the total number of particles times this W evaluated at this saddle point. So, obviously, if I want to convince myself that entropy is extensive, all I have to do is first evaluate this theta star phi star and then insert it into this W, and then convince myself that this W is intensive. In other words, that if I scale the system, it is not going to change at all. So, the question is, can I do that? But before that, let me point out to you that what are the important implications. Suppose I were able to convince myself that entropy is indeed extensive. So, what would be the profound implication? Why am I so concerned about the extensivity of entropy? The reason is because it really leads to some remarkable identities that you should probably already know from thermodynamics, but I am going to refresh your memory. So, one of them is called the fundamental relation in thermodynamics. So, suppose so imagine a gas. So, I will get to the gas later. I have been talking about marbles on a staircase, but that is not really a classical ideal gas. We will get to that later, but suppose just for a moment I will appeal to your knowledge from your earlier coursework. So, if I am talking about an ideal classical ideal gas, you know that the entropy really depends on the total internal energy, and there is something called the volume of the system, which we have not encountered yet, because I am talking about marbles on a staircase till now. So, but eventually I will be encountering volume as well. So, if I decided to scale the total internal energy of the system, the volume of the system, and the number of particles in this fashion, then extensivity simply means that the entropy is just scales the same way. In other words, it is also lambda times the original entropy. So, if this is really the case, if entropy is indeed extensive, then all you have to do is realize that to get the original entropy, it is the same as differentiating this with respect to lambda. So, if I differentiate with respect to lambda, this becomes S, and so S becomes the derivative of the scaled entropy with respect to the scale itself. So, it is really peculiar, but this is an important observation, because I can use my chain rule of multivariable calculus and rewrite this as there are 3 independent variables here, u dash, v dash. So, each of them depend on this lambda. So, there is an implicit dependence on lambda. So, I can partially differentiate S with respect to u dash, then differentiate u dash with respect to lambda, and I do that the same with v dash and with n dash, and then finally I set lambda to 1. So, if I do that, I get this nice relation. But now I have to appeal to your knowledge of thermodynamics, and then you will recall that in thermodynamics the absolute temperature is defined as the reciprocal of the derivative of the entropy with respect to internal energy. Why this is a meaningful definition of temperature is something I will get to a little later. So, it is not some arbitrary definition. There is a deeper physical reason for why temperature is defined like this in thermodynamics. So, we will get to that a little later, but for now let us assume that you know this from your knowledge of thermodynamics. So, similarly pressure is defined as that this temperature times the rate of change of entropy with volume. Of course, when I differentiate with respect to volume, I have to keep the total energy and the total number of particles fixed. So, if I differentiate with respect to total energy, I have to keep the volume and the number of particles fixed. And lastly, there is something called chemical potential. So, the chemical potential is similarly defined as temperature times the rate of change of entropy with the number of particles. So, there is a sign convention that you define it with a negative sign. So, these are all from your earlier knowledge of thermodynamics that I am not going to presently derive, but I will be deriving them maybe few slides down the road. So, if you allow me to do this, if you allow me to write this, then I am going to be able to insert this into these relations and derive a nice formula. But note this in small print I have written here that we are measuring temperature in this course in energy units. So, which is the same as setting this Boltzmann constant to unity. So, normally we kind of entropy is actually defined as Kb times the number of ways of doing this. In fact, this formula is engraved on the tombstone of Mr. Boltzmann himself. And this of course, it would be ridiculous if this Kb was set equal to 1 on his tombstone, in which case you will not be paying a tribute to him at all by setting his famous constant to 1. So, it is a good thing they did not do that in his tombstone, on his tombstone, but I am going to do this in this course. I am going to set Kb to 1 because it is annoying. I would much rather measure temperature in energy units and get rid of this altogether. Alright, so now I am going to insert all these identities into this relation, which is obtained from chain rule of multivariable calculus, and I get this result, this beautiful result that says that the entropy of thermodynamic system, specifically a gas in this example. So, it does not have to be an ideal gas, by the way. I have made no commitments about whether the gas is ideal or van der Waals or any other type of gas, but it is just a gas. So, because there is a volume associated with this and there is a number of particles and there is a total energy. So, the entropy of this gas is nothing but the total energy divided by absolute temperature plus pressure times volume divided by absolute temperature minus chemical potential times number of particles divided by absolute temperature. So, from here it is obvious that the extensive quantities are entropy, the total internal energy, total volume and total number of particles, and the rest are intensive. So, the other three, pressure, temperature and chemical potential, are intensive. So, I am going to stop here. And just to give you a heads up, so from the next slide onwards, I am going to discuss I am going to explicitly derive formulas for the entropy of a Bose gas and a Fermi gas, but then in the thermodynamic limit. So, I am going to work only in the thermodynamic limit, and I am going to use my saddle point or the method of steepest descent approximation to get hold of a nice closed formula for the entropy of a Bose gas and a Fermi gas. So, hope you will join me for the next hour. Thank you.